Hey, what's going on, everybody? Today we're going to be talking about uniformly accelerated motion. And it's just going to be a little bit of an overview of the equations and how we use them. And you can see some practice of me setting them up. But mainly, if you want a little bit more of a conceptual overview with this stuff, I have some videos linked. They're not by me, they're by a really good physics guy. And that channel's Flipping Physics. So, uniformly accelerated motion. What does that mean? This applies anytime that the acceleration is constant. That means it's not changing. It could be constantly zero. It could be, a constant like 2 meters per second every second. It could be whatever. But as long as the acceleration does not change, then we're happy here that it's constant. Okay. The other thing that we want to talk about is the equations. So a little overview of the equations. There are 4 different equations. There are 5 different variables. So let's go over the variables real quick. So there are the 5 motion variables that we're always going to be using, right? Delta x, remember that is change in position. That's what we call displacement. And then obviously if something's accelerating, it's going to have 2 different velocities. So we got an initial velocity and a final velocity. We have an acceleration, and there's always time involved. So here are our 5 different variables, and then there are 4 different actual kinematic equations that we're going to use to represent all of this motion. And there they are. Those are the 4 different kinematic equations that we have to use. We have, final velocity squared equals initial velocity squared plus 2 times the acceleration times displacement. And then this one right here is the one that ends up getting used probably more often than not, but really it just matters, what do we have to work with? All of these things are our tools, and it's our job to figure out what do we have, what do we need, and which one of these are we going to pick to actually use. So without further ado, let's go ahead and I will show you the process that we're going to use to set these up. So let's scroll on down. So we have our first example right here. I'm going to move that thing down. Sample problem 4.5. In your packet, this is page 19. So this is set up for you already on page 19. And we have a moving van increases its speed from 15 to 40 kilometers per hour in 20 seconds. What is the acceleration of the van? So first step. I want to draw like any diagrams or anything that I have. So diagrams can help. Plus, it's always fun to draw. So there's a horribly drawn van, right? It's got some vroom lines. Initially, we got 15 kilometers per hour. And we have a final velocity of 40 kilometers per hour. Time is 20 seconds. So this is all, a little more than we need. But now we make our table. So the big thing that we want to do is we want to, I also want to show, what direction is positive. I forgot that one. So so in this problem, there's a giant line. To the right is going to be the positive direction, right? The velocity, acceleration, displacement, all those things are vectors. So it's very important to know which direction is going to be positive. So we have to the right is positive. Now, let's make a motion table of everything that we have. What does that mean? That means that I need to basically just make a list of everything that I have to work with. So, what do I have? I have displacement. So I like to just write everything to start. Okay, and then I draw a little line going down. And then we can keep track of everything that's here. Go through the problem and see what we got. We have a car. It doesn't tell us anything about displacement, but what it does say is it says it starts at 15 kilometers per hour. It says it finishes at 40 kilometers per hour. And we are trying to find the acceleration. So I like to put a little question mark where, to signify whatever we're trying to find. And then the time is 20 seconds, right? So I have initial velocity, final velocity, acceleration needs to be a part of it so we can solve for it, and then time. So I need to pick one of those equations that has those four things in it. So if I go back up to my little list, right, which one of these has those four different variables in it? And it ends up being, let's see, this one, right? Final velocity, initial velocity, acceleration, and time. So that's the equation that I'm going to be using to figure out what the acceleration is. So now we just plug and chug. It's the beauty of it, right? Now I have, so I start with that equation. I like to solve for the variable first. So I'm going to move around all these variables until I solve for acceleration. So I would subtract velocity on both sides. Then I would divide by time to solve for acceleration. And there you have it. Now we can plug in the values that we know. All right, and when we get this, you don't need to worry about units too much. What I have is a final answer of an acceleration of 25 kilometers per hour over 20 seconds, right? So if you actually figure that out, let me grab a calculator real quick. Drag it down here. Well, I just screwed everything up. All right, that's not going to work. 25 divided by 20. What is that? 1.2. Yep, 1.25. So this would be 1.25 kilometers per hour every second that van is moving. So every second that van is changing its velocity by 1.25 kilometers per hour. Got it? All right, next one. Solving for displacement. Anita Life is initially at rest and sprints to a speed of 10 meters per second in 3 seconds. Okay, so she's initially at rest. She gets to a top speed of 10 meters per second and it takes 3 seconds. So that's an initial velocity right there. There's a time involved. What distance did Anita cover? So we're trying to figure out, it says distance, but we're being asked like how far. So what we have to work with here is displacement while she was accelerating. Okay. So let's make our little table and keep track of what we have. All right, we're trying to solve for displacement. We know the final velocity was 10 meters per second. Initial velocity was 0. That's what initially at rest means right there. We don't know acceleration, and we know time was 3 seconds. So I need to pick an equation that has these 4 variables in it. So now we just need to go back up and take a look at what those were. All right, which one has displacement? Which one does not have an A for acceleration in it? Well, the only one there is the very last one. See that? Boom. Okay, and now remember I'm trying to solve for delta x. It's already solved for delta x, so all I need to do is go ahead and plug and chug. So let's go. 1/2. Initial plus final velocity is 10 plus 0 meters per second. And the time is 3 seconds. So that's 10 meters per second times 3 is 30 times 1/2. 15 meters. Because over here, if we look at units, right, a meter per second times a second lets us know that these things cancel, and so we would be left over with just meters. Okay, so the displacement here, how far did she move while she was accelerating? 15 meters per second. And then it also asks this question, what would her velocity versus time graph look like? And so we can just sketch out that graph real quick. All right, we have a velocity versus time graph. So remember, this is velocity in meters per second. This is always time. And it said she started at rest. So that tells me that she's going to start here at 0. And 3 seconds later, she was at 10. So let's do our seconds. 1, 2, 3. And then we need to have her at 10 meters per second by the end of it. So at 3 seconds, she needs to be at 10. And it's just as easy as me knowing she is constantly accelerating. The graph of this velocity graph will be linear. And so I just need to draw a line right there. Okay, so if you were, this is the equation way of solving this stuff, but let's say you read this problem and the graphs really make sense to you. You are totally able to just graph this out real quick. And if we want to find displacement from a velocity graph, all you need to do is find the area under that curve. And that area should also give us 15 meters, like exactly what we solved with the equation. Okay, so the actual velocity versus time graph looks just like that. Okay. All right, moving on. Sample problem 4.7. I believe we are on page 20 now on the backside. Sample problem 4.7, multiple questions about motion. What is the distance traveled by a car going a constant 2.5 meters per second if it travels for 11 seconds? So here's one of the things with this. So we want to know what's the distance. All right, so we're asking, in this case with these equations, we're trying to find how far it goes. So displacement. It's going a constant 2.5 meters per second. So what does that tell us? That tells us the initial velocity is 2.5. That also tells us the final velocity is 2.5, right? And the other thing that you can infer from that is that the acceleration, if it's constant velocity, the acceleration is equal to 0. Okay, so that's also something that we can figure out from that. And we know it's going 11 seconds, so that's the time. So just as always, let's keep track of what we have. Okay, displacement is what we're trying to find. Initial velocity 2.5, final velocity 2.5, acceleration is 0, time is 11. So here's the deal. We have 4 of these variables. We're trying to find the 5th one. Pick whichever equation is going to do that the easiest for you. Okay, and what ends up being is probably the easiest equation for us to use is that one that we used last time. V plus V naught T, right? So we just plug and chug in here, 1/2. V plus V naught, 2.5 plus 2.5 meters per second times 11 seconds. And what does that give us? 2.5 times 11, 27.5 meters. Okay, now depending on whichever equation you pick to use, should be the same answer no matter what. Okay, so whatever equation you use, you should get that answer right there. Now, part B, what's the car's final position if it started at 0.35 meters? So this isn't like an actual pick an equation type one. This is just kind of seeing how we feel, dealing with all of the kinematic stuff. So remember, displacement, that's change in position, right? That is equal to the final position minus the initial position. Okay, final minus initial. It's the change in position. So I know right now the displacement was 27.5 meters. And we're trying to find the final position, so I don't know what that is. But I know it started. So right there, there's a little algebra problem for us to solve. How far did it go? Or where did it finish, right? So if I solve for that, I can add 0.35 to both sides and get the final position as 27 point. Hope I did that mental math right. All right. Cool. We got one more. elevator drops a rock from a bridge. What is the rock's displacement after 4 seconds? So rock's falling. This one takes a little bit of mental math. We haven't done this lab yet. If I'm still here, we will have done this lab. If I'm not, then you just got to take my word for it. But when things are falling, they accelerate at a rate where they speed up 9.8 meters per second every second, and they're speeding up going down. So when we write this as an acceleration, because it is going downward and because that's the number, here's what we usually do to make our lives a little bit easier, right? We say the acceleration when things are falling. So we call this the acceleration from gravity. So a little g. Sometimes you will see this written in textbooks just as g. That's the acceleration from gravity, all right? The acceleration from gravity is about negative. That's because of that little downward piece right there. That downward piece means negative. And 10 meters per second every second. Why 10? Because this number makes our mathematical lives a whole lot easier to do than 9.8. 9.8 gives us weird decimals all over the place. 10 is a beautiful number that we can do a lot of mental math with, all right? So it's a little bit of rounding, okay? But that's where it comes from. So that is when falling objects accelerate downward. They speed up by approximately 10 meters per second every second that they fall down, all right? So let's see how this plays into this problem. Elevator drops a rock from a bridge. Well, if we have somebody dropping a rock from a bridge, okay, drops a rock from a bridge, really long arm right there. And when she's holding the rock, it has an initial velocity of 0 because you're holding it, right? Then when you let go, now that rock starts to fall and accelerate. It falls further and further every second, right? And so we know when you drop implies an initial velocity of 0, okay? Right there. That's super important, right, for us to know. If you drop something, you're holding it, it's not moving, so it starts with a velocity of 0, okay? So let's keep track of all of our variables that we have. Drops a rock from a bridge. What is the rock's displacement after 4 seconds? So we're trying to find displacement. We know the initial velocity is 0 meters per second. We know the time is 4 seconds, but that's only 2 pieces of information. There's one there that we know, but they don't like explicitly tell us in the problem. And that's that original piece we talked about. Anytime something is falling, we know it is accelerating at a rate of negative 10 meters per second every second. Okay? So here I have these values. I can go ahead and take a look at my equations and see, okay, what is the one equation that doesn't have a final velocity in it, that has these other 4 variables in it? And so when I do that, I see this kinematic equation right there. And now I can start plugging and chugging. Now, what do we know? Make your life easy. We know the initial velocity is 0. So this whole chunk, if I plugged in a 0 right there, 0 times anything is 0. So that whole chunk goes away. So this whole equation just got a little simpler looking, right? I'm trying to solve for displacement, so I am good to go right there. And now I can just plug and chug. Okay. Multiply everything out, do a little math, a little abracadabra, and we get, let's see, that is 5 times 16. What is that, 80? Not approximately, it is 80. So equals negative 80 meters. So why negative? Let's break this down, because this is how far it's fallen, right? But we want to break this down. So what does this negative mean? Well, in this problem, right, usually when you're doing physics problems, we got down means negative, up means positive, right? So if my object displaced negative 80 meters, that means it displaced downward. So it finished, right? So it finished down below where it started, So that's what that negative means. That's an important number. And then the 80, obviously, is how far. So remember, displacement is a direction. So that's why the negative and the positive actually are very important. They give us the direction that the thing is going. All right. So that is exactly how we do those. Now, there are some more problems for you to go ahead and try out. So do your best. If you have any questions, make sure you email me. All right. Hopefully ask me in class. Hopefully I'm there. But email me if you need something. I will talk to you all later.